Let me welcome another speaker. It's Oleg Shelajev, and Oleg is a developer advocate at Oracle Labs working on GraalVM, the high-performance embeddable polyglot virtual machine. He organized also VirtualJUG, the online Java user conference, and GDG chapter in Tartu, Estonia. In 2017, became a Java champion. He has a topic about cloud-native Java microservices with GraalVM. So, welcome, Oleg.
Hi. Am I not
Hi.
muted anymore? Excellent. This is perfect.
No.
Hi. Thank you very
Yeah.
much for the introduction. It's an honor to be here. I really,
Really enjoy.
it's a pleasure to be here. Right. I'm a developer advocate indeed, as you mentioned, and you can find me on the internet. I go by @Shelajev, and it's an honor to I think it's almost the last slot here, so I'm closing this. Just before the conference started yesterday, I think I saw this promotional, somebody tweeted about the conference or posted on LinkedIn, oh yes, this is an amazing conference. There are at least two amazing speakers, the Baruch and Josh, right? And this GraalVM dude from Estonia. So I'm a company of excellent speakers, and people know me that I am from Estonia. So we're very good.
Yeah, great
right.
stuff.
So if I understand correctly, we have 40 minutes. 40 minutes. Is that correct?
Yeah.
Yeah. Okay.
Sure.
I see myself. So let's go right into this. Let's go fast and hard. This is a very intense session. At least I plan it to be. Full of interesting information. Just like the fans of the faster Java release cadence, right? Many releases, a lot of information in a short time span. So, cloud-native Java microservices with GraalVM. This is a technical presentation, so do not make forward-going business decisions based on the contents of this. This is a necessary precaution. And also note that native image, which is a big part of this presentation, is currently under the early adopter technology, which doesn't mean that it's experimental. It is supported, but it can undergo significant changes further. So be mindful of that. If we talk about GraalVM, and if we want to talk about how GraalVM can help you cloud-native deployments and with your applications in the cloud, we have to talk about what GraalVM is in general, because it's a very large and versatile project, and it can help your application. It has different use cases, right? So at the heart of GraalVM lies what it is. It's a runtime, right? You can use it to run your applications. You can use it to run your Java applications, or there is a number of other languages that it supports. But all in all, it's a runtime that you can use to run your applications. And at the heart of that runtime, what differentiates it from other things that can run your applications is the just-in-time compiler, the state-of-the-art optimizing just-in-time compiler, which can be used as the top-tier JIT compiler in OpenJDK, in Hotspot, in Java Hotspot virtual machine, right? So, and that is the most straightforward use case of GraalVM, and you can use that on your microservices, in the cloud, on premises, anywhere where you run your Java applications. You can just enable them to run on GraalVM, and because of the just-in-time compiler, probably they will be running faster, which is kind of very interesting because everyone loves fast software. Nobody likes slow software. So this is kind of very cool, right? And then based on the same compiler, the same compiler can be also used not in the just-in-time mode, right, where it activates at the runtime of the application, but it can also be used as a ahead-of-time compiler, which we package as the native image technology, right? What it does, it takes your application, takes your Java bytecode, and then can analyze that and compile that and produce the native binary for your specific platform. That binary will be standalone, so it will not depend on the JVM availability at the deployment site, and it will be rather small in size, and it will exhibit the performance profile of native applications, right? So it will start very fast because everything is precompiled, and it will use smaller amount of memory, right? So the memory footprint will be lower because it doesn't need to, for example, allocate memory for the infrastructure of the just-in-time compilation technologies, and then doesn't need to track some class files metadata, doesn't need to interpret classes, anything like that, because all the code is precompiled. And now in both modes, with the JIT compiler and in the native image mode, you can run the other languages as well. So GraalVM supports running other languages such as JavaScript, Python, or WebAssembly. Obviously, all the JVM languages, so you can throw in the same list of supported languages Scala and Kotlin, and Clojure. And the Clojure community I like personally very much. They're usually incredible engineers, and it's a nice language as well. So if you have a chance to, and if you want to learn a new language on the JVM, Clojure is a good fit. That a little off top there, right? So, but the GraalVM offers you those three main use cases and values, right? JIT compiler for the faster runtime, native image compiler for the different performance profile, which suits cloud deployments very well, and the polyglot API, which you might not use, right? You don't have to use it, but if you want, you can use it for the spicing up your application with other languages. And we're going to talk about mostly the native image compiler, because this is something that you want to use in the cloud. And when you build your native image, your microservices, you want to let native image optimize that if you want to deploy those. There are some trade-offs and there are some things that you need to know about that, but we're going to go into more details later about that. So in general, if you want to just get acquainted with GraalVM and you haven't looked at the project before, there are a number of resources that we produce. For example, I really like this GraalVM quick reference, which you can find on the GraalVM team blog, right? So medium.com/GraalVM. There are a number of articles by the team, and one of them is the quick reference. You can kind of gives you a high-level overview of what you can do with GraalVM, and also some command line options that you can explore that show exactly, like, not just some configuration options, but they show the potential and capabilities of GraalVM, which is kind of cool. Before we go into native image, let's talk about the compiler, because I know the conference, the Cloud Builder Conf, is a dual conference for two audiences, right? There is a Java track and there is a .NET track. And I'm not sure how much people watch both tracks at the same time, but if any .NET people are watching, this is a little something for you. And also, if for everyone who is mostly has background in Java, like yours truly, you can also maybe appreciate that this little tidbit of information. The compiler in GraalVM is really, really good. And how I know that it is good? Because, well, we run a ton of benchmarks. But how you can know that it's really, really good is because even the .NET runtime developers think that are kind of sort of impressed with the GraalVM compiler, right? So there's one, of course, not universally, right? It's just an anecdotal piece of data, but it's kind of cool issue that highlights some of the very important qualities of the GraalVM compiler. So there was an issue in the .NET runtime GitHub where they took a piece of code in Java, run it with GraalVM, rewrote that in .NET, right, in C#, right, and then run it, and it was slower. It was much, much slower because the GraalVM compiler is that good, right? And then even when they try to rewrite the same piece of code using structs rather than classes and objects, right? So structs will not allocate memory that much. It was still slower, and that's an interesting issue just for the reference there, which highlights how good GraalVM compiler can be at some things, specifically even outperforming some other solutions wherein they could be using a more advanced data structures, for example, or memory layout. So that's a cool tidbit, right? If .NET people say something is cool in the Java world, that's something is really cool. That's at least how much I know. But that is, of course, an anecdotal data. Why we know that the GraalVM compiler is really, really good is because we run a ton of benchmarks. And then on average, the average temperature in the hospital comes out that GraalVM compiler outperforms the corresponding JDK OpenJDK releases by quite a bit, right? So the performance, of course, difference varies based on the workload and the exact data and the exact code paths and data inputs and everything. But in general, it is faster, right? So, and it's not just faster, it also evolves faster. So like during the last year, for example, GraalVM compiler Specifically, it was the state of the art. It was already really, really fast, outperforming other solutions, but it also got, like, for example, in a year, it got like 6% faster across like a very large, well, a very large kind of set of benchmarks and important workloads that we run. So make a note that maybe even if you don't want to use native images, you can use the GraalVM compiler from the GraalVM distributions, right? So a number of projects did that. So one of the use cases was the Oracle Cloud telemetry services migrated to that, saw the peak performance improvement, saw the garbage collection time reduction, specifically probably because the escape analysis optimizations in the GraalVM compiler are so good. It reduces the pressure on GC, making your application less prone to spending a lot of time in GC, right? Twitter moved their Scala microservices onto the GraalVM compiler, and they saw the benefits, and there were a number of presentations across the old conferences, venues, and jugs by Chris Challenger, and he's not unfortunately with Twitter anymore, but by him, he was on the VM engineering team there, and by other people, how they use that and get benefits and results and spend less on hardware. Also, apparently, GraalVM is a really, really good virtual machine at runtime for running your Minecraft servers, which is kind of funny because we didn't try that, right? Minecraft is not one of the benchmarks we run, but apparently it shows itself very, very nicely. So if you're running Minecraft, think about that. Run it on GraalVM. Right. So this is the JUG compiler. And how do you get started with that? It's very, very simple. You download, you unpack the archive, you may put it on your path, and you run it, and it's all nice and clean and smooth. It's really, 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 really simple, right? So what I can do here, I will show you my cloud machine here, which runs my Java, and I do Java minus version. And you can see that my Java in the past by default is GraalVM Enterprise Edition. And yeah, it's based on Java 11. So we're currently providing builds based on Java 8 and Java 11. Some experimental builds are coming up, probably based on JDK 16, but that is currently in the very early stages. And then potentially we will keep up with the current JDK releases as well. So you can use that for all your purposes. For example, here I have my ID. Right? And I just want to show this is the IntelliJ IDEA running on the same cloud machine through Projector project, right? And if I use about, you can see that the runtime version there is, it disappears. But the about version there is based on the Java hotspot with Java MCI, which is exactly the GraalVM version that I'm running there, which is kind of cool. So you can run that. I claim that my idea, because of this, is faster, but that is a subjective measurement. I didn't run any benchmarks. It just feels a little bit faster. Right, so that's how you can use it. Let's go back to the presentation kind of. Now, we know now that we can run our microservices or our Java applications on GraalVM. Now we would like to make them cloud-friendly. And in the cloud, what I mean by the cloud-friendly, I mean that their performance profile should be of the application that we want to run in the cloud. So specifically, some applications, what we want when they talk about fast, we think the peak throughput, right? We want our application to warm up, and then we won't touch it for months, and it will be running, crunching its data, serving its users, and it will be really, really nice. So in the cloud, we don't do that. We deploy small applications into ephemeral containers and ephemeral virtual machines, and they get destroyed and recreated and scaled up and down like all the time. And then we do more and more deployments. So the essential characteristics of the cloud are the startup and the memory consumption, because we want to pack our application into the smaller containers as much as possible. So we can stuff those small containers into larger VMs or our Kubernetes clusters. And then since we're paying for the resources that we're consuming, we don't want to have like a large buffer around the application that is needed, for example, only for the startup purposes, right? We want to constrain the resources very neatly. So using GraalVM native image can give you native application performance. So for example, for the simple application, and simple, it's a relative term, right? It's a microservice that has some HTTP like server, and it can accept the requests, and then it can maybe process and send them to the database or write them into Kafka or something like this. The startup times are in milliseconds, and you can see the red bars here are GraalVM native image, and the blue bars here are the corresponding application running on the, I think, OpenJDK of the same version that the base JDK in the GraalVM distribution was used here. So you can see startup is really fast, and the memory consumption is much, much smaller. So you can literally run a microservice that will consume, like, I don't know, 60 megabytes of RAM. That is the total RSS of your project, of your application. So it's not just heap, it's the whole memory that your application is using. Right, so that's that. Why those two specifically are important? Because when we talk about the cloud, right, as I said, we want to optimize for a different use case. So the high-level comparison between JIT and AOT is approximately this, right? So the JIT-based solution will be better at the peak throughput, right? The JIT has the best visibility into your application, into its runtime and workloads, so it can optimize, and then it also can de-optimize your code. So the peak throughput will be potentially higher, and also the inverse of that is that the maximum latency will be also better. So the latency will be smaller because the throughput is higher, but also because for example, other solutions like GC solution in the JIT mode are more sophisticated, right? So for the ahead of time compiled mode, the native image, your startup speed will be incredible. Your memory footprint will be much, much lower. Your packaging will be much, much more convenient. For example, a small application that does some processing can be just like a command line application can be like as low as 3 megabytes in size, and a small microservice can be like 10 or 20 megabytes in size, right? That's the full Docker container, and we're going to look at that a little bit, right? But because AOT compiler cannot speculate that much, right? Because the native image at runtime, it lacks the capacity to de-optimize and optimize again, because it has no infrastructure to deal with the bytecode. Then the peak throughput could be lower. The latency could be also less ideal, because, for example, your garbage collection implementation could be simpler, so you can't hit the stop the world pauses. So there is a trade-off right here. There is a trade-off. You can pick one or another, or of course some deployments you can use both if you want to, right? Because you can scale them individually, but you kind of sort of can pick. And very luckily, GraalVM offers you both solutions, right? So you can run your applications in the JIT mode, and also you can run your applications in the other mode, right? In the ahead of time compiler mode, right? So that's that. You can run them. You can pick and choose. Right? How the application packaging works, right? The native image utility, right? You feed your application to the native image utility. What it does, it analyzes your application, the libraries that you're using, the JDK classes, and also the runtime components from the GraalVM project called Substrate VM. All those things are written in Java. So actually, the whole GraalVM project, most of the GraalVM project is written in Java. The compiler is Java, the native image utility is Java, the components of the runtime that go into native image is Java. All of that is Java, and so is your application. So all that bytecode, that set of the bytecodes, right, can be analyzed using the same technology. So all those bytecodes are taken in, and then they are analyzed. So the analysis is iterative. So it finds which classes reference other classes, and then which applications, which classes reference other classes, which objects are created, and so forth. So then the native image runs the initialization of those classes. It figures out the object graph, the universe of the objects that are created using, like, when those classes are initialized and run. And then when this analysis kind of reaches a fixed point, right? So you analyze and you do the whole snapshotting thing. And if it doesn't change after the iteration, you know that you analyzed everything and that you know that you've seen the whole code that will be used at the runtime of your application. Then that code gets compiled, and then the data, the object that we created during the analysis, during the initialization of your classes, those are written out in the image heap of your application process, right? So that is the native binary, native executable that will be the output. What you can do is that you can take that and you can run it just like normally as you would do with the application, which is kind of interesting. And of course, because a lot of work that usually happens in the beginning of the runtime has been done before at this build stage, right? The performance profile will be different. Right? So when you start your application and you start make it do some business work, right, the CPU doesn't spike. The CPU only is used for processing those, like serving the business value to your clients, right? When you run it in a JIT mode, when you start your application, it needs to initialize things, it needs to load the classes, it needs to start preparing things, it needs to verify the classes, it needs to start initializing some data structures, start initializing data structures and infrastructure for the JIT compilation, interpret the bytecodes that you're running, and then serve the request. So you can see on the right there quite a bit of red, which is the CPU measurements for JIT process. And both of those examples served a couple of requests, and it's a Micronaut application. You can see that ahead of time compiled native image based solution takes just like 3 megabytes of RAM and just does work when it's hit with the requests. And the JIT based solution running on the Java hotspot VM initializes and uses quite a bit of CPU, and then everything else, right? So now we get to more interesting parts, right? So, and this is something like so to speak, what I wanted to have like as the core of the application of this presentation, right? Sort of the best practices which I've seen being used in different projects, and some of the best practices are actually the best practices, and some of the best practices are just the normal practices, but they like answer some questions that were that that are created and kind of like some misinformation or some misunderstandings that I've spotted in the community when people talk about native image. Right, there are some things that they're not like, you need to understand some things about how native image works, and then you can use that effectively, right? So if you don't understand certain things, you can still use it and sort of effectively, right? And then you can by trial and error stumble into the correct path, but it's less obvious how to do that, and then you might be frustrated because it's not trivial, right? There is an analysis stage, like the build stage and the runtime are two different stages, right? So you need to adapt your mental model of how your application like runs in general. So that's how. And one of the main complaints and one of the main things that people kind of talk about is the configuration for the dynamic features in the language. So for example, reflection, proxies, GNI, usage of the resources, usage of serialization, and so on. Right? Those things are dynamic. Like the code that they will be invoking when you use a reflection or when you try to access a resource. The actual code or the actual resource will be determined at runtime, right? So you can literally pass the name of the resource or the name of the class to your application as a runtime as a parameter, I don't know, from the HTTP query. And based on that information, you can decide which classes to invoke. Obviously, the static analysis that we perform on build time cannot figure out that statically because that information is just not available. So the solution cannot include those classes in the final binary. So you have to provide the hints to the compiler saying that, oh, I'm going to use those classes and those methods for reflection access. For example, I know that my model will be served through Jackson and it will be using reflection to serialize and deserialize my model into JSON. Maybe I need to include my model classes into the final native image. That would make sense. So you can allow the reflection access by providing a configuration file, which is a JSON file that is very straightforwardly interpretable by a human person, right? And then, but it's a little bit tedious to write, right? So what you can do, you can literally there's a Java agent that you can run and then execute your application on the JVM, and it will output the configuration for you. And I want to show you this on an example. I think I can still show this here, right? So let's go to the application, right? I have my very simple application here, main Java, right? So it's a super simple application. One class, it just computes some Fibonacci numbers, but in the main method, what it does, it computes the Fibonacci numbers, and then it outputs them and writes them in a file, and then it deserializes the same file, so it gets back another list, right? And then we control and check whether those lists are equal, so whether they contain the same numbers, right? So this is the deserialization feature, and it will work on your hotspot VM out of the box because it allows the deserialization of random arbitrary classes. Native image doesn't allow deserialization of arbitrary classes. So if what I need to do, I need to run this specifically with, let me just copy that command. Copy that command, right? Which is sort of play from the current slide. Very nice, very nice, very nice. We're back here, right? So I will remove the config directory because I don't want that, and I will make the config directory because I like that as well, right? So, and now I will run Java minus run. I will do config inf native image, and then I will just do jar and my main class. Native image run. I'm just running my application. Minus p, create the directory. So, and then we run our application. So it does output the things that we asked it to output, and it also created the configuration files in my application. So if I do, if I look what's in my config directory, you can see there are a bunch of files created. So the reflection configuration and the resource configuration, and proxies and GNI, all those accesses to those features are traced and recorded during the execution, and you can merge a number of configurations provided with this Java agent. So let's look at the config meta inf native image serialization, because our application just uses serialization, so the other files are here empty. You can see that it creates the JSON file that is necessary for configuration for my application. Now, when I build native image, I can specify where I have my serialization config or reflection config, or I can rely on the fact that the meta inf native image directory from the class path, from the root of the class path, will be taken in automatically. So I can just do native image, and then I can do class path, and I just do config, right? And then I do main, because that's my main class, and I run this, which will take a moment. Wait, main, what is this? Right, excellent. So we add the current directory to the class path as well. So this is the process that runs, and this is the process of compiling our application, and not just this one class, but also the classes from the JDK standard library that we're using, compiling them to the native image ahead of time. So we want to create this main class, main executable that we're going to run, and that will be running, right? So if we will not provide the config for the serialization, obviously that will fail, because the serialization will not be the code for serializing those objects and those classes will not be included at runtime. But since we did, we can see that our application is here. It's 14 meg, and we can run it. We can just run it, right? Run it, and we get the same output as we did on the Java, and we can time it, of course, and we can see that it takes no time to do this. It's not a lot of work, right? So, but it also doesn't take any time to run any initialization of the virtual machines and so on. So that's how you do the configuration for those dynamic features. And yes, you can claim You can claim that, oh, you need to run the actual code pass in your application, but you sort of have to run those code paths anyway because you run your tests. So test is one of the best places to collect that config. When you run your application tests, you can attach this agent and it will provide the configuration, and then you can merge those JSON files and then get a large configuration set that you can apply when using native image. So the all code paths that are covered in the tests, for example, will be included. Of course, you can edit those files as well. So if you know that certain classes are necessary to be like open for reflection, so to speak, right, then you can just run it and specify that manually. Or you can rely on your framework to run this, right? So that's the tracing agent, and that is a very important part. And if you're in Dub, you can always run the native image through that. You can always run through that, right? Another thing is that you always can look what the native image is doing under the hood, right? One thing is that building native image, the process is actually a Java application, so you can use the Java debugger to kind of step through the execution and see what exactly is happening. For example, if you want to see what initializes a certain class in your application, what you can do is you can just go on the dashboard. You can just set a breakpoint into the class and then step through with the debugger and see the stack traces. Another thing, how you can see what's happening inside, you can use the dashboard feature. The dashboard is an online tool that we are storing from the GraalVM.org website that you can generate some you can generate some data dumps, so to speak, and then you can import them, and they will be processed on the client side in your browser, and you will see the diagrams. For example, which classes and packages take the most size, which classes and packages which code snippets take the most size, and which objects on the heap take the most size. So you can effectively navigate what needs to be optimized if you want to optimize, and then cut the size of your executable quite a bit. Right? Also, what you can do, you can use just the universal packer for executables, UPX utility, and compress your application, and you'll get a much smaller result. And I can show you here, right? So this is my main executable. What I can do, I can show the strings output, strings main, right? And I can grep. Don't have to grep, right? There are a number of strings. There are a ton of strings. And you can also see that there are, besides just actual like binary strings that are like the some encoded data, but there were also like actually string values. So if we do grep svm right? So for example, you can see there are a bunch of configuration strings inside of our executable, right? And if we just, for example, take the VM version, you can see, for example, the GraalVM version that we were used to create this native image. So all those are actual strings in the binary file, so you can compress them, obviously, and then run that, which is kind of cool. I think it is kind of cool, right? So if you want to package this now into Docker, there are a number of options that you want to do as well, right? You want to use Slim-based images because the executable actually doesn't depend on well, you usually want to use Slim images, but you don't have to even put your Java in there because the native executable, native image is standalone, so you don't do that. Another option is where you might want to use the distroless base images, right? This is the base image that doesn't contain the operating system. It just contains the libc and some other necessary files for your application, because the all the native libraries that you're using will be packed into the native executable. You can use this static executable with dynamic libc command line option for the native image that you can just pass to the native image executable utility, right? And then the pack the file that you have to the thing. And you can also use the from scratch Docker images. So you can statically link everything into your native executable. you can use the muscle implementation of the libc, and then you just, that is a fully standalone file. You can throw it into from scratch Docker image and it will work, right? And I can just show you Docker images, images. I want to show you some things. So I have a bunch of applications here, which is, we are looking at those three, for example, that I created. It's a small microservice built with Micronaut, and it uses 3 different Docker images. So Slim uses Oracle Linux 8 Slim, and it's 133 megabytes. Distroless is much simpler because it doesn't contain the operating system, and I can do dive times web distroless. I can do this. Dive is a utility to analyze the Docker images. So it will fetch my image, and then it will show some data about that. Right? So you can see that there are 3 layers. 2 of them is just the basic command line, not command line, libc utilities, like the binary files, and then our application, which is 22 megabytes, just added to that file, right? So you can see the app there on the right, right? And the image size is 40 meg, and it's a very efficient image. And also the same way I can show you the static, right? Which is the from scratch image. It doesn't have anything. It just literally has our application, and it's 22 megabytes in size, and I can still run it. I can do Docker run, and then remove, and then what? Primes web static, right? I need the ports. I need the ports. Let me just put the ports here, right? -p 80 web static, boom, it runs. You can see it starts up really fast, and then I can, let's say in a different command line, I can SSH. Oh, I'm already here. I don't need the SSH. Excellent. So I just can curl HTTP. Show you that works 80 primes random up to 100. Right, so you can see that every time I invoke this, it gives me primes numbers, and it's a very simple application. But I just want to show you that it's actually working, right? So I stopped the application and it stopped responding to me, which is kind of cool, And you can do this with different frameworks. So like this was Micronaut application. You can do Spring. I have an example of a Spring application here in my IDE. To be honest, this is using a recent project called Spring Native. So you can see that it's a normal Spring application using a normal Spring controller, and the whole magic is there in the POM XML. So it uses the Spring Native project, which you can enable from the start.spring.io, currently in beta, and it, stuff like that, right? And it uses the native image plugin by the GraalVM team to create things, and you can see that I configured it to use static and muscle C as my libc implementation, and after that I just build it, and my Docker file here is very simple, and I would be able to run this application the same way. I could actually run this application, right? What if we do Docker images? Oh boy, we need SSH again. Let me just come back and I do Docker images. And then I have do you see something here? Primes Spring from scratch, right? So I can do run, but this would be out my Spring application. Boom, it runs, right? It takes 40 milliseconds to run this, and I can run the same curl command, and you can see that I'm still getting prime numbers. So now this is the Spring application packaged as a native image, and now it's 19 megabytes because it was packed with the UPX running in there. Right? So this is kind of cool. So we are getting closer to other best practices and things that you need to know about native image. One thing is you want to configure the memory for native image, right? So this machine that I have here, right, is like a proper workstation, 100 gig of memory, 16 cores, right? If I don't restrict the resources for my native image, right? If I just running in a Docker, for example, right? This Docker, the Docker container that I'm having here, right? So this one, right? It has access to all the CPU, and you can see that it also has access to all the memory, right? So when I will try any load tests or to see how much memory it takes, it will be allowed to take as much memory as it pleases, right? Because I'm not limiting those resources. So be mindful of that. And then because you're not limiting the resources, it can think like, oh, I can take whatever. And it will take whatever, because that's the most efficient way to run if you're allowing those resources, right? So you want to limit the memory. And there are a few options that you want to know. Is like obviously XMX, XMS, the new generation XMN. You can look at what happens with the GC, with print GC, verbose GC. This is just the same options as you use for hotspot. And also what you can do, you can bake in the maximum heap size, right? Which will be used unless you're providing the explicit characteristics there will be used for your application. So you can build an application that by default says, I want to use like 50 megabytes of RAM. Very nice and neat, right? So that is something that you need to remember if you want to use that. And also, since we're talking about memory, right, there are some options available in the GraalVM Enterprise Edition of GraalVM. So you can enable the G1 GC, which will allow you to run with the better latencies. And it is also an adaptive garbage collection, so you don't need to manually actually tweak the memory settings. So you can just say like, oh, this is G1 GC and go. And also you might want to use the profile guided optimizations, which is then will add an extra step to your build process, right? So you need to build an instrumented library, you need to feed it relevant workloads and collect the profile, and then use those profiles to create the optimized image, optimized binary. So that's what you are supposed to do and what you're recommended to do, specifically if you're using GraalVM Enterprise Edition, which is the product by Oracle, but well, people are using that, so there is no shame in using that. And there are a number of very interesting things that you can do with native image, specifically because it can take a Java application, build an executable, or a shared library. You can build a shared library. So, for example, this way, the GraalVM polyglot engine, right, and the GraalVM infrastructure is built into the multilingual engine, which is the feature of the Oracle database, which allows you to run JavaScript in the database. Kind of like you would run like a Postgres, not Postgres, of course. What is it called? PL SQL procedures, and you can run them now written in JavaScript based on the GraalVM infrastructure in the database, which is kind of cool, right? You can also use it to speed up your command line applications, for example, such as build tools, right? So there is a few interesting options. I'm going to go to this. I'm going to go to this URL actually. So SBT, which is a Scala build tool, has the I don't know how much you can see, has the SBT is a build tool, right? What it does, it can run the daemon, right? The server using normal Java, using JIT mode, and then it can run the SBT native client, which will connect to that daemon and then pass the request to compile something, or build something, or to run something. And that client is the native image of a Java application. So it starts really fast and it gives you this instant feedback you can see in this video. And this is the ASCII cinema of the development. Like those are on the PR that was merged into SBT, right? You can see that running a few tests takes no time, even though this is Scala and even though this is SBT, because because the daemon is running and warmed up, and the client takes no time because it's a native client, which is a spectacular thing, right? There was also a similar effort for Maven, which is the Maven D project, which creates a Maven daemon, and then the client for that is a native image, right? So when you type Maven something command, right, like it will start really fast and then just tell to the daemon that, oh, do this. And the daemon is ready to do that because the daemon kind of lives for executing those tasks, right? Because you probably warmed it up already. So this is something just like you might want to look into and so on. So the other projects in the ecosystem also kind of are looking into supporting native image and enhancing the use cases for developers that want to use native image. So a number of libraries, for example, the AWS SDK, since some version recently, uses and embeds the support for native image, right? So that config that you saw for serialization and the reflection, that can be put into jar file, and then when you consume that dependency, you will be able to have that config out of the box. And you can see the measurements there for like a sample workload are much improved, which is specifically very useful for cloud deployments and like function as service deployments and so on, right? So libraries are doing that. I think, yeah, HTTP clients and so on. Recently, Lightbend blog, someone on the Lightbend blog wrote how they rewrote their Kubernetes clients from Go, because that's how you usually write Kubernetes clients, to GraalVM native image, to Scala, and package it using GraalVM native image, right? And they get the same performance stability, and they're very happy with the results because they love Scala more than Go as a language, and because it integrates better with their ecosystem of other tools, so they can like unit test it in conjunction with their other applications and so on. So this is some use cases that you might want to use native image for. And then on top of that, you can do more, right? So you can include the Java on Truffle, which is the GraalVM implementation, sort of a Java based on the Truffle framework, the same way we support other dynamic languages like JavaScript. And then you can run that and you can build it into the native image as well. So sort of like this. So in the JIT mode, you have Java code that executed dynamically, and the hotspot is pre-compiled. In the ahead of time compiled mode, native image, you have Java code and the VM components all together pre-compiled. And if you include Truffle, then your code and the Java and Truffle code and the Truffle and the JIT are pre-compiled, but then still you can run some Java code dynamically, right? And yeah, so that's it. If you want specifically to look into using native image, there is another quick reference that you might be interested in. Or you can try the sample app. So you can go into github.com GraalVM demos. You can see the apps there, and you can try this and that, and you can talk to us. And definitely, you want to look into this. You want to join our Slack. You want to join maybe our mailing lists, or follow us on the socials. And of course, you want to download GraalVM and try it for your code and for your applications and projects. That's all for me. I hope there are some questions. I hope people are still with us, and I hope you liked it.
I really liked it. It's a really great presentation, I think, and a really great topic. Also, we have questions. We have two questions from our guys, probably from the one guy. Yeah, it's the first question from the Konstantin. It's about GraalVM Enterprise has a pricing model per CPU. Does Oracle have a pricing model for serverless?
Right. So currently, the pricing model for GraalVM Enterprise is that GraalVM Enterprise is included in the Java SE subscription model. So when you're buying Java SE subscription from Oracle to use Oracle JDK, you get the entitlement to use GraalVM Enterprise Edition. So you can just have that. This is one pricing specifically. That pricing, like, so you cannot buy GraalVM Enterprise standalone, I think, currently. And not a salesperson, but I think this is the information that I have, that you buy Java C subscription for that. And pricing for that is indeed CPU based. So for the serverless, it's a little bit more complex calculation. One thing that you might want to note is, so like, in all honesty, I don't know if we have the pricing for the serverless solutions. You want to ask your Oracle representative or send us an email about that. But if you have the Java C subscription, you can use it, of course. And if you run your workloads on Oracle Cloud, for example, I know that GraalVM Enterprise use is free of charge on Oracle Cloud. So yeah, there's definitely some serverless solutions that you can use for with GraalVM Enterprise free of charge or without the per CPU kind of payments, right? I hope this answers, and sorry for not being salesperson here.
Yeah, probably it's good to see, probably in an Oracle site. Yeah, and we have also a question also from the Konstantin about, is GraalVM going to support the garbage collector?
Right. This is the very interesting question. So, and the background of this question is that you can run your Java applications on GraalVM without code changes, right? It's because it's a compatible. It includes a compatible JDK, right? So you can just change the path runs. However, there are some components of the runtime that needs to be aware of the JIT, or that JIT needs to be aware of. One of them is the GC, because the GC might want to keep their own like invariants to what the memory and the heap and the system properties look like, right? And if JIT compiles your code to machine code without respecting those invariants, right, everything will break. So the combination of the JIT and the garbage collection needs to be integrated. Currently, GraalVM supports the G1 GC and parallel. So the ZGC is not supported. It just will fail to start if you specify both options, saying that, oh, this is an incompatible combination, right? And it needs work. It needs work to integrate those two. So it's not like that becomes a question of prioritization, right? So currently we're supporting what we have binaries based on JDK 8 and 11, so which are not, I think, ZGC kind of target releases. If we move towards forward, that would be a more like interesting and urgent question, but it requires work. So, and I personally, I'm not sure on which side of the project the work needs to be done. So it might need to be done in the OpenJDK where ZGC resides, right? And or it might be done on the compiler side. But somewhere the work needs to be done. It would be very interesting, and I think we'd be happy to investigate that as a team. Or if you want to investigate that, you can join the conversation on GitHub, and if you have the applicable skills, you can definitely talk to us. Right, we are an active open source project, and would love to talk about that. So in the future, probably yes, but currently it needs work. Right? That's the answer.
Yeah, great, and probably Konstantin can join your team to develop this feature. Yeah, also we have another question. Have you tested Shenandoah GC?
Right. Personally, I've tried Shenandoah, not with the GraalVM builds, right? Because again, the GC and the JIT compiler needs to be, the combination needs to be integrated. So doesn't work with Shenandoah, right? It doesn't work with Epsilon either, right? So it would be very interesting to support Shenandoah, right? So we do have a collaboration with some Red Hat engineers working on various aspects, both on the native image and both on, I think, the for the ARM Arch64 backend, there were commits that are coming from the Red Hat engineers. So that is something that we need to just collaborate on, right? And I think there were some people looking into that. Roman Kenke, for example, I think I saw some tweets from him that he's looking into that at some time ago, but I don't think that actually resulted into anything substantial. But yeah, we just answer it needs work.
Okay, great. So thank you, Oleg. I think we don't have any additional questions. Probably I will have one. So probably from my side, when I try to, probably when I have application, I have probably microservice architecture, and I use usual JDK, yeah. And do you know when I need to go to the GraalVM? Probably when I have some problems with the performance or something like that. So how I can take GraalVM that can solve my problems, probably something like that.
Right. Like, so you don't have to wait until you have problems to use a faster runtime, right? Using a faster runtime is just beneficial in any case, right? It like what it might make sense is to consider, like, if you have like a performance test suite, it might make sense to consider running them on both versions and to see the performance impact of that, right? But you can just also just migrate and run your application on that. In the best case, it will be faster. Well, in the worst case, it might be slower as well, of course, right? Depending on the workload and specifically how well it optimized. It is being optimized on C2, which is the default top-tier compiler in OpenJDK, right? But you can always test and try, and then use the faster option that you have, right? Like, you don't have to wait until you are actually on the, like, fast is a relative concept, right? So like you almost never actually like fast. You are always faster than either some version of the same application before, right? Or you are faster than the service level agreements requires. So you might have some say like, I need to serve my request under 1 second, right? And you are fast if you're just better than that threshold, right? So of course, the more code you add to your application, the easier it is to slip like behind the threshold and become kind of like slow, right? So, but as long as you're under that, it's all okay. So the thing is, with the faster runtime, you have more leeway into adding more code. You can also use maybe more abstracted code. So GraalVM compiler is really, really good at the code that uses all kinds of abstractions. So it's a more sophisticated compiler than C2, and it includes like sort of the escape analysis is better. So you can use objects without worrying about the allocation costs, or without worrying that much about allocation costs, right? So yeah, you just migrate and work with that. If you're talking specifically about native image, I would recommend you starting with using native image specifically on the greenfield projects. So when you start a new project, you might want to think about, okay, yeah, let me run it as a native image. I want to pack it into smaller Docker containers, give them less memory, pack them neater in memory, and then you start from scratch, and then you use a framework that supports native image, because starting from a framework that doesn't support that, like, or some random code base of like unclear age, probably you will stumble upon some code paths there which are either like still stumble upon the features that are not fully supported by native image, or that require configuration that you don't fully understand how to provide, right? So the GraalVM team itself is one of the largest, probably one of the largest like users of the native image utility and technology, right? All our languages are compiled as native images, so you can run them without running the JVM, right? Also, the GraalVM compiler itself, by default, is compiled as the native image, a shared library. And when you run GraalVM, the JIT compiler there is actually a native image, a native executable built with native image of the GraalVM compiler written in Java, right? So we compile our stuff with native image, and we know that it sometimes needs to, sometimes it requires configuration, but we also know how to provide that. So if you're starting from scratch, maybe you don't want to go head first and like trying to figure out the exact configuration that is needed. Like, though using the tracing agent, it's much easier than before, but still, right? You need to understand like the built-in utilization, and that there are two lifecycle stages and so on. So on the greenfield project, starting with a framework like Spring, using Spring Native or Micronaut or Helidon or Quarkus, uh, uh, that will work much better than if you are running your applications currently on, I don't know, WebSphere, and you're like, I want that converted to native image. That becomes a little bit more challenging.
Okay.
Right?
Okay, great. Thank you very much for your answer. For me, it's more clear, so I can take a look on the the stuff, so we can probably integrate it with one of my projects. Yeah. So thank you, Oleg, for this article. It's really great, and I think have a good night.